All right, hello everyone. Welcome to the 8th lecture of the quarter. So today the main topic will be magnetism. So you probably already started talking about it in DL. So I'm gonna in today's lecture kind of summarize the main ideas that you'll be looking at in the next week. Okay, before we do that, let's review a little bit what we have learned about electric fields, electric forces and voltages and so on. So what we saw, one kind of main idea is, initially when we started talking about this, we kind of focused on one point charge. So there was one source, and we thought about what kind of electric field does it generate and what kind of voltage does it generate. But in reality, sources are often a complicated combination of multiple charges or continuous, an object which is continuously charged. So what we looked at is this principle of superposition, where if you have several sources that contribute to your total electric field or total voltage, then what you have to do is just simply sum the individual voltages for each charge that is present, or sum individual electric fields. Now this is just a scalar addition, adding a bunch of numbers together. Some of them could be positive, some of them could be negative, because voltage could either be positive or negative, but it's just a sum. Where here it's a little bit complicated because electric fields are vectors, so here you're adding vectors together. In one dimension, adding vectors is just about thinking whether the two vectors are pointing in the same direction or in the opposite directions. If they're in the same, you just add them. In the opposite direction, you subtract them, making sure you define what is a positive and what's negative direction. But in 2 dimensions and 3 dimensions, it becomes a little bit more complicated. So make sure you review your vector algebra before kind of moving on with this material. In higher dimensions, you have to break each vector into its x and y and z components. Normally in this class, we just look at 2-dimensional problems and then, add by component, and then think about how do you then express our total vector in terms of magnitude and direction and so on. All right. Another thing I want to review is the electric dipole. It's one specific system we looked at. And the reason I want to do that here again is because it connects very nicely to magnetism when we get into that material. So, again, when we started talking about electric fields and forces, we always thought about, there's this individual charge sitting there in space. In reality, most objects or molecules and things like that in nature are neutral. So there's no net charge. But it does not mean that they still don't interact electrostatically. And the reason that they often do is because although overall there's no net charge, there's sort of a positive and negative end to your object. And then because of that, there could still be interactions. There still could be, the positive side is feeling, let's say, an attraction to something that's more negative, and the negative side is feeling an attraction to something that's more positive. So when you have your object that is not kind of symmetric charge-wise, there's a positive and negative side, we can always simplify that to an electric dipole. So even if there's 3 charges like what you see here, we can say, well, let's define this electric dipole, which goes from the negative side to kind of the average of the positive sides here. And in DL, you worked out a little bit more mathematically how to calculate it for various charge configurations. So we define this electric dipole vector, sometimes known as the electric dipole moment, which will point again from the negative to a positive side. It's a vector because it has a direction. And then the magnitude depends on these various factors like the charges present and the distances. Okay, so how do we think about the electric field now generated not just by a point charge, but by electric dipole. So let's review point charges. So for point charges, for example, as a positive charge, we saw that electric field lines, so here talking about in terms of lines, they start at positive charges and they go off to infinity. Also, we made the relationship between voltage and electric field, that voltage decreases in the direction of electric field. So you see these equipotential lines, which are circles around our point charges. There, the voltage is decreasing in the direction of the electric field. So if we started here with 4, then we went to 3, 2, and 1, and so on. Another important feature here is the density of these lines. So both the density of equipotential lines and the electric field lines is proportional to strength. Well, so the density of electric field lines is proportional to the strength of electric field, and the density of equipotential lines is proportional to the rate of change of your voltage. So over here, the voltage is changing at a slower rate compared to over here where it's much more dense. Okay, so now for negative charge, things are just, everything is kind of reversed. So negative charge, the field lines, they end at the negative charge. So the electric field points towards the negative charge, but these characteristics such as electric field and voltage, those are still the same, that voltage has to decrease in the direction of electric field. So you see that these numbers, now the voltage is negative, so it's getting more and more negative towards the negative charge. So these are point charges. So now think about it. If these 2 point charges are separated far in space, they don't really feel each other because electric field gets weaker with distance and it gets weak pretty fast. But as we move them together, creating this dipole, you can think about like this field line now, which normally when the positive charge is all by itself, now because the negative charge is close enough to it, it would feel it, so it kind of tried to go to infinity, but then would drop back down to the negative charge. The same with this one. It would, instead of going off to infinity, it kind of would feel this and then drop here. And then this electric field line, which starts at the positive charge, which kind of just end at that negative charge. So just kind of think about moving these 2 charges closer together and sort of merging their electric field lines. And what do we get? We get exactly this dipole electric field lines that you have seen now, I think, several times in DL. So this is what it looks like for a dipole. And it has, in a sense, a similar structure to them as just point charges, except again, now these field lines are kind of bending towards the, from positive towards the negative, but the density is still preserved here. They're less dense far away, more dense nearby. And again, the field lines, they go away from the positive and towards the negative charge. Now, how do we go from here to drawing equipotential lines? So you can kind of think about it in several ways. First of all, you can think about it in terms of the superposition. So for example, right at the center between the negative and positive charge, you're the same distance to each charge, but the 2 charges have opposite signs. So when you add the 2 voltages, they will cancel out. So the central line would represent 0 voltage. And then, so let's take a look here. And then as you go closer to the positive charge, the voltage is going to be increasing because it's going in the direction opposite of the electric field. Now, when you're going towards the negative charge, that's the direction where the electric field is pointing, so your voltage is going to be decreasing. So to go from 0 and increase, this has to be, let's say, 1, 2, and 3. Again, I'm just choosing this increment of 1 volt. It doesn't have to be that way as long as the increments are the same between 2 neighboring equipotential lines. And then to decrease towards this direction, it has to become negative. So -1, -2, -3. And now they're no longer they can no longer be circles, because another rule that we've learned is that equipotential lines have to be perpendicular to electric field lines, and because these are not straight lines, you cannot get perfect circles. Instead, you get kind of these oval-like shapes as you make your equipotential line, represented here by these dashed lines, and try to make them, you know, perpendicular to your electric field lines. The density is still very telling here. You see that over here where the electric field has the largest magnitude, the rate of change of voltage is the largest too, because the density of the equipotential lines is the greatest, where that density decreases going outward. All right, so this is the electric dipole. Another thing that we thought about is the potential energy of an electric dipole. Remember, when there's a potential, when we're talking about force or potential energy, we need another object or something, another source of that charge with which your object interacts. So if we're talking about not internal forces, but is there force acting on our dipole, to have that force, we need something else. So when we're thinking about potential energy of a dipole, what we're really asking about, if there's another object which generates, so now we have another source, the dipole is not our source anymore, we have another source which generates some electric field. So these electric field lines, this is just an example, it doesn't have to be this one, but here it shows some constant electric field. Perhaps there's an infinite plate sitting somewhere over here, which happens to be positive if it's on the left. If it was on the right, it would be negative. Okay, so we have this external electric field. So the question is, what is the potential energy of our dipole in this electric field? And it turns out that it follows this relationship. So it's related to the strength of the electric field, the strength of the dipole, and also the angle theta between that dipole moment and the electric field. So in other words, and we know that in nature, things like to minimize their energy, or another way that we've been saying it is that force points in the direction of decreasing potential energy. So there will be a force on this dipole in such a way to decrease its potential energy. How do you get the smallest number here? So if you think about the cosine, it can be, the biggest value you can have is -1. Then you can have, let's say, 0. The largest value it can have is +1. And when cosine of theta is +1, we get this negative sign. So that's when potential energy is minimal. How do we get the cosine to be +1? When theta is 0. So in other words, when theta is 0 is when this dipole moment is lined up exactly with an external electric field. So dipoles tend to line up with electric fields. And if you think about it, if we imagine the source of this electric field as being this infinite negative plate that's sitting right here, what does that mean? It means that the positive charge of the dipole is attracted to the negative plate, while the negative side is repelled. So wants to be as far as possible. The positive charge wants to be as close as possible. So that's what makes it kind of align up with that electric field in that example. All right. Okay, so now we're going to shift to magnetism, but then we'll come back to this picture in order to draw these parallels between magnetic fields and electric fields. And you'll see that there will be a lot of analogs present there. Okay, so now we're going to start with something that seems very different, you know, in everyday experience. When you think about magnets, you think about, you know, let's say two metallic things that are sticking together. When you think about electricity, you think about static that gets created when you sometimes try to open the door and you get shocked, or if you go down a slide in a playground. So, you know, they seem like very different phenomena. But as we look at this deeper and deeper, we will see that actually the two things are very much so connected. And in fact, initially when scientists and physicists were studying this, they did think of them as two separate forces, the electric force and magnetic force. But as we dug deeper into the behavior of these forces, eventually physicists realized it's actually all one force, and they defined it in one, what we call now the electromagnetic force. So that's why you often hear electromagnetic as one word, because really it's ends up being one type of force. But at this stage, we're still going to look at them as two separate phenomena. All right. So we'll look at what are the similarities and what are differences between something that's a magnet versus something that's a charge. So magnets always have two poles. In other words, you know about like the north and the south pole of a magnet, but what does that mean? Well, it means that, what does it mean for it to always have two poles? Is that if you take your magnet and you break it in half, it's not that you create a north and a south pole magnet. So with charge, you could do that. If you had a dipole, which had a positive and a negative side, and if you separated that dipole, you would have a positive charge sitting here and a negative charge sitting here. There would be two separate charges. That doesn't happen with magnets. So if you take a magnet and you break it, what you end up getting is two magnets, each having a north and a south pole, such as this. And you can keep on doing that. You can keep on breaking your magnet, and you'll never get just one pole of the magnet. You can go all the way down to the electron, to some elementary particle, and you see that even that particle is like a magnetic dipole. It has a north and a south end. So far, although physicists really like the idea of nature being symmetric. So, if there's an electric, what we call monopole, there's only one charge separate. So physicists would like to believe that there's also such a thing as a magnetic monopole. So in the sense that you could get just a north and a south pole. So there's still a lot of ongoing research on this as far as trying to find the single pole or the magnetic monopole, but there hasn't been any success. So at least where we are at this stage in our understanding of magnetism is that there is no such thing as a magnetic monopole, and it's always a dipole. And we just happen to call them the north and the south pole. And very similar to charges, where like charges repel, opposites attract. The same thing is true for magnetism. So a north and a south pole will attract, two north poles will repel. So I'm sure you've all played with magnets. You take two magnets, sometimes they stick together, but if you flip one around, what you're really doing is you're flipping the orientation between the north and the south pole, and then suddenly they repel. So that's kind of this idea about like poles repelling, opposites attracting. Like charges making electric fields, poles generate magnetic fields, and we call them, we use this capital letter B for magnetic field. It's also a vector, so that's why it's B with an arrow on top, which is vector. So because there's no such thing as a monopole and there are only dipoles, these field lines cannot be straight lines. So we saw in my review that I just did with your single charges, when you had the single positive and negative charges, you had these straight field lines, which were, field lines started at positive charges, ended at negative charges, but they went off to infinity or came from infinity. There's no such thing for magnets because there's always the other pole present. So instead of lines, you get loops. It loops around the same way that the electric dipole will always loop around, because your field will always find the other end. And the way we define these field lines, this is just by convention, is that they flow from the north to the south pole. So as you see, this has very much so the dipole structure. Actually, I realize this picture is not ideal because the density of field lines is not very apparently getting less, but like the electric field, the magnetic field also gets weaker with distance. So, you know, if you take two of these magnets that attract each other, they're not attracting far away. You have to bring them close together to really feel that pull. So the magnetic force also gets weaker with distance. So, you know, you can kind of see the density of field lines getting weaker. Remember, these are field lines. So to get field vector, you have to choose that point and look at the tangent to that point to get your magnetic field vector at a good particular point in this magnetic field. So again, they flow from north, but because there's no single north pole, these lines will always bend towards the other pole, which is the south pole in this case. All right, so how do we actually even can view this? Well, you can imagine that if you take this magnet, which has this north and south pole, this is, you can think of it as our source. If you put a bunch of little compasses around this magnetic field, compasses themselves, they act like mini magnets. What they will do is they will, as you could see in this picture, they line up with the magnetic field. So if you look carefully, you really get kind of this loops that you see if you follow the direction of the arrows where this compasses point. So you could see kind of right above the magnet, it's almost parallel, same here. So you really can trace this magnetic field. And you could also see, for example, if you look at this one, you see that the south side of the compass is close to the north. So if the field line, as we've defined, points away from north, then the north side of this compass will line up with that field. So you can think of the compass as its own magnetic dipole, which is lining up with the magnetic field of the source, the same way that electric dipole was lining up with an external electric field. Here we have a magnetic dipole lining up with an external magnetic field. And you know, why does that happen? Because opposites attract. So the south side is going to be the one closer to the north, and the north side is going to be away from the north. Where here on this side, we have north side, which is getting attracted to the south side of this magnet. All right, so here's kind of a picture that really draws parallels between our electric dipole and our magnetic dipole. So here, as we just kind of described, we had an external magnetic electric field and an electric dipole, and its potential energy was given by this equation where it's minimized when the electric dipole is lined up with an electric field. Now this is this analogous diagram here. Now imagine we have our magnetic dipole, and we use little letter m for that. It's a vector. And if we have our little magnet, the direction of the magnetic dipole points from south to north, the same way it pointed from negative to positive here. And if we put this magnet in an external magnetic field, kind of like we were putting our compass near that big magnet, what's going to happen is this magnetic dipole will line up with the magnetic field. So the north side of this compass will point along the line of the, will point in the direction of the magnetic field. So you see these two equations are very similar, except instead of electric dipole, letter P, vector P, we have magnetic dipole, vector M. Instead of electric field, we have magnetic field, which is B. And again, this cosine theta with a minus sign in front tells us that the magnetic potential energy is going to be minimized, which is where the force will point when theta is 0. So that's when you get the most negative or the smallest potential energy, magnetic potential energy that you can have. All right, so we all know that the Earth is magnetic. That's how we determine using our compasses where north and south is. So what we do, like in that picture, instead of imagining putting a magnet, our Earth itself is a magnet. And we take our compass, and the north side of the compass, if we look back at this picture, the north side of the compass, where should it point based on this? Because opposite poles attract. It should point to the south end of our source. So when we take our compass out on Earth and our compass points north, we say that's where the north is, just because I guess it's consistent. We chose that convention because it's consistent with, okay, compass points north, that's north. But really, where's it pointing when it points north? It points to the south end or the south pole of our magnet. So in other words, the geographic, what we call the geographic North Pole, what we call the North, is really the magnetic South Pole of our Earth. So it's a little bit confusing, but kind of a fun fact to learn. And so, you know, here is kind of a toy, let's say, picture of how the magnetic field of the Earth looks. Of course, it's a three-dimensional, you know, it's a big sphere, so it's three-dimensional, so you can imagine these magnetic field lines like coming down and then out of the board and kind of circling around. So this is a really nice looking kind of dipole like magnetic field lines. In reality, it's actually much more complicated. So here's kind of a realistic depiction of the field lines of the Earth. And another interesting thing that it turns out that the magnetic poles of the Earth, they go through reversals. It doesn't happen very often. I think they have predicted that at this point, it's only been about 200 times in the entire life of the Earth. And the last magnetic reversal happened about 700 plus thousand years ago. So it doesn't happen very often. It's also really difficult to predict. It doesn't seem to have very periodic structure, but it does happen. So this is just kind of a depiction, a prediction of how the poles would look like during the reversal when the Earth is reversing its magnetic poles. It would be kind of all jumbled up until it reverses. Then it might last a couple of hundreds of thousand years and then reverse back. So it hasn't always been in such a way that our geographic North Pole has been the magnetic South Pole of the Earth. It's been opposite as well, back a long time ago. All right. So, okay, so we've been talking about this magnetic fields as some kind of mysterious things, because, you know, with electric fields, it's pretty clear. We know about charges. We know that, you know, at this point, we've learned about atoms, and that atoms have positive charges in their nuclei and negative charges, electrons orbiting around. So we know where that electric field comes from. But what exactly is magnetic field? I mean, we've defined them because we've played with magnets and we see that there's some force. But what is really the source? You know, what is causing these magnetic fields? And it turns out that it is those same charges that cause electric fields, except it depends somewhat on their behavior. So it turns out that it's moving charges. So these electric charges, you know, are same positive and negative electric charges that create magnetic fields, but they do so when they're moving. So when the charges move, well, you can think about it on a very small microscopic scale. the electrons themselves, for example, their charges, themselves have dipole moments, and electrons spin. So it's that motion that causes these magnetic fields. On a macroscopic scale, when have we seen charges moving is when there's current. For example, when there's a bunch of charge flowing in a wire in a circuit, we call that current. Why do we call that current? Because there's a bunch of electrons all moving in one direction through that wire. So you see, we're kind of starting to connect these two very seemingly different, by observation, forces or physical phenomena such as electricity and magnetism. It really turns out that they're come from the same source, which is charges. So let's first look at the macroscopic charge motion, how that causes magnetic fields. So it turns out if you take a wire, so here's a depiction of a wire which is carrying current, and the way this wire is oriented, you can imagine that this current is flowing upwards. And if you put a bunch of our little compasses here around this wire, it turns out that they are affected by this current. So that shows that, what does that tell us? That this current is creating a magnetic field because these compasses line up in a very particular way around this wire. If the only thing that was present in this situation, so we can never get rid of the Earth's magnetic field because we're doing all these experiments on Earth. So if this wire was doing nothing, all these compasses would just line up with the Earth's magnetic field and would point north, what we call the geographical north. But they don't behave that way when there's a wire nearby that carries current. And you could see that the north side of these compasses, they kind of create these circles. Another interesting thing that happens, if we took another wire where the current was moving downwards now, relative to how we place these compasses, now you see that the direction is reversed. Now the north is pointing clockwise if we look from above, counterclockwise if we look from above from a current that's going up. So first, before we go a little bit more into this, there is a right-hand rule I want to introduce. When did we see right-hand rules before? We saw it in 7b when we're trying to figure out direction of torque and things like that. So right-hand rules are good for direction. So because this direction of magnetic field depends on the current, we have this just right-hand rule to help us figure out which way the magnetic field goes. So remember, in the case, let me actually go back here. In the case of current going up, we had our magnetic field which was going counterclockwise from above. So this is sort of a picture of this. So how is this right-hand rule going to help us? So what we do is, and this is where, I wish I was in lecture so I could really demonstrate this, but you put your thumb upwards in the direction of the current, as this picture demonstrates. And then you curl your fingers around, and the curling is what's going to represent the direction of your magnetic field, or the magnetic field lines here. So you see thumb up, and that's how you get the curling in this case, is if you look from above counterclockwise. So that's exactly how you get this circle. So this is how you would use your right-hand rule. And you could see that if the thumb was pointing down for the second example with the current going down, then your fingers curl clockwise, so you get that reverse direction. So very often when we look at wires or at current, this is no longer a two-dimensional problem, as you see, because we have our current which is going up and down in this page, and these field lines that are going around. So there isn't just a field right here, where this whatever projection is drawn, there's another field up and another field up. So you could imagine there's an infinite number of these circles that you could draw around the electric field. And also, around this wire, these circles which represent your magnetic field lines. And in addition, this magnetic field gets weaker as you go away from this wire. What that means is that you can imagine drawing kind of another circle here, which is a farther distance apart, and a third one even farther, so the density is getting less and less of these magnetic field lines as you go away from the wire. So because it's a three-dimensional system, and if we really want to more focus on the magnetic field lines, what we often do is we would like to change the perspective on how we look at it, just because it's difficult to draw these circles that are coming in and out of the board. So here's the same situation, but it's a top view of it. So all we have done is we've shifted the view. So now you imagine this wire, instead of going up and down on the screen, it's going in and out. So let's remind ourselves of this notation. So remember, we had torque and we had our right-hand rule, and with that, things became three-dimensional, so we had to worry about vectors pointing in and out, kind of similar situation here. So out, the way we draw the vector coming out, it's a circle with a dot. So it's the tip of your arrow sticking out, where in, if your arrow is going into the board, you get a little X at the end. So here, if we go back to this picture, imagine you're looking the top view, so you're looking down at this wire, so the current is now coming out at you. So now again, this wire is just going in and out of the board, current is coming out. And now we can still apply this right-hand rule. So now instead of your thumb up and down, the thumb is out of the board. So you should really practice this as you're watching this. And now my fingers are curling this way in such a way that now our circles are in the plane of the screen and they're counterclockwise. So these are your magnetic field lines, and you see again the density here, the fact that this circle, the third circle here, is farther apart from the second and the second from the first, shows that the magnetic field is getting weaker. So here we represent it a little bit more mathematically. So here's just to show the other case. So in this case, the current is down. If we apply a right-hand rule to this perspective, the thumb goes down, fingers curl clockwise, so you get these clockwise circles, and as you see, this is much harder to draw. You have a bunch of them, they're getting farther apart. Now, if we look at the top view, in this case, the current is going into the page, and you see these, when you're looking from the top, all these circles, they like collapse onto each other. So they overlap, so then you just need to draw one set. So the right-hand rule applied here, you stick your thumb into the board, you curl your fingers, so you get these clockwise circles going this way, and they're getting farther apart to represent strength of a magnetic field. So if we want to actually draw the magnetic field vectors, what do? As we did with the electric field, you choose a point, you draw a tangent line. So right here, the magnetic field points north. Right here, because the field line is going that way, it points south. Right here, it goes west. Right here, it's kind of southeast. Now, the lengths here represent the magnitude. So here, because we're closer to our wire, the field lines are more dense, you get a bigger magnitude. So the arrow is bigger, here less dense, arrow is going to be shorter, smaller magnitude. All right, so mathematically, how does this magnetic field vary with distance? It varies as 1/r. So here's the equation, but it also depends on the current. So the stronger the current, the stronger the magnetic field, the farther away you are from the wire, the weaker the magnetic field. So it's proportional to current inversely proportional to R, which is distance away from the wire. And then there's a new constant that we introduce, which is called mu naught, and that's what it equals to right here. So this tells you about, again, magnitude of a magnetic field. Magnetic field is a vector, but this part is just the magnitude. How do we figure out direction? Using the right-hand rule. So we kind of separate the two concepts. The equation gives you the magnitude, right-hand rule gives you direction. All right, so this is, okay, so there's more. Now, imagine, let's look at a slightly different system and apply our same right-hand rule. Instead of just a long wire, continuous straight wire, imagine now we have current which is going in a circle. So this is not magnetic field lines anymore. This is a wire now. So I know it's confusing because before we had these circles representing magnetic field lines. So forget about that for a second and think of this circle here with this arrow. I should have put maybe an I for current, is now a wire, which is circular with current, which is flowing counterclockwise. So how do we figure out the magnetic field on this current loop? Well, you can do it at various points. So let's look at that point right at the top. You can use our right-hand rule. Remember, thumb goes in the direction of the current, which is going to the left. And then we curl our fingers around. So what that means is that above the wire, the magnetic field is going into the board. Then you curl around. So imagine this is my wire. So into the board above the wire, then you curl your fingers around, and then below the wire, you see my fingers are pointing towards me. So that's why above the wire, we have a little circle with an X. Into the board, this is out of the board. And you could do that at all the points around this wire. So like right here, it would be the same idea, right? Wherever you are, you're gonna be into the board on that side, outside the wire, and or outside the loop, and out of the board inside the loop. So if you kept on going, you find this type of structure. So now let's flip our perspective. So we often will do this with when we're thinking about magnetism. So now this is this view. Now imagine we take our loop and we rotate it. So what we see now, because remember, these represent circles. They're going into the board and out of the board in a circular way. So if we rotate it around, we actually find something like this. So see, that's that same circle, except now our loop now is pointing out of the board and going in. So this is kind of a physical depiction of a wire carrying loop. And these little things represent like little pieces of metal that are ferromagnetic, so they can get magnetized in an external magnetic field, and you actually see them forming. You might have seen stuff like this in science museums, where you see actually them forming, arranging themselves in this dipole-like structure. So you see actually your dipole. So it's as if this has nothing to do, you know, you would think with magnetism, but suddenly it's as if your wire which has current becomes a magnetic dipole. And here, when we look at this picture, first of all, you know, inside the loop, that's when they're most dense. That's the field is the strongest. It's getting weaker outside. Also, by looking at this particular lines of the magnetic field, we can figure out which way the current is flowing because we can use our right-hand rule. So we know that inside the loop here, the magnetic field points to the right. So that means that if we put our thumb down and then curl our fingers, so inside the loop, fingers are pointing to the right. So that tells us that the current is flowing from the top down, so kind of in this direction along that loop, if these two are representing the same system. So it's going into the board at the bottom and then coming out of the board at the top. So by looking again at this dipole, at this magnetic field lines, we can figure out the direction of the current. Okay, so why do we care about loops? Well, let's make an interesting system where we take our Y and we keep on making many, many loops. So these are all connected. And if you were in DL, you would see stuff like this. Unfortunately, you won't be, but you'll get to take a look at some cool videos. So if you keep on doing this, what ends up happening is, again, principle of superposition. So you could think about each loop creating its magnetic field. So now you have multiple sources of this magnetic field, which add up, and they add up in such a way that you get this very strong magnetic field inside. This is known as a solenoid, this particular structure of multiple loops. And what's interesting about it, what's useful about it, let's say, is that inside the solenoid, it's as if you get this constant magnetic field. So if you, of course, at the edges now you get this loops going around, but inside it's as if you get these parallel field lines. So it serves a very similar purpose as the infinite plate did, where that created a constant electric field. Here we get a constant magnetic field, and you can also get a very strong magnetic field. So what is this magnetic field? Depend on the solenoid. So the more loops you have, N is the number of loops, so like the number of these that you count. And then it depends on the length. So you wanna, if you wanna maximize the magnetic field, you wanna squeeze this in together as much as possible. You don't want to space them out. So it's, in a sense, this N over L, you can think of that as the density of your loops. And the more dense they are, the stronger will be the magnetic field, and then it depends also on the current. So if you want to create a strong magnetic field, one little wire normally won't do it, unless you put a lot of current through it, but you know, wires have capacity, they can't handle very high currents, so this is a good way to create a strong magnetic field. And when do we use strong magnetic fields? Well, one example is in MRI machines. So if you ever wondered why an MRI machine has this cylindrical-like shape, well, it's because of this, because it's a solenoid. So inside of this MRI machine, there is this superconducting wire, so you don't need to worry about exactly what it means. It just means it has very low resistance. And there's about 8,000 of those, that wire's looped about 8,000 times. So you could kind of just imagine this. And pretty high current, 100 amps. So if you remember back in 7B, when you're measuring current with a, you know, simple circuit of light bulbs and batteries, you are getting, you know, maybe an amp or less even of current. So this is very strong current. So what happens is, inside this solenoid or this MRI machine, you get a very strong magnetic field. And for a typical MRI machine, it ends up being around 1 Tesla. This is, you know, one example of the magnetic field. So that the strength, the units of magnetic field that we use is Teslas. And if you compare that to the Earth's magnetic field, it's this much bigger. So 10 to the power 4 times bigger than the Earth's magnetic field. So it's pretty strong. And you know, what does MRI stand for? Magnetic resonant imaging. So what happens basically is your body gets put in a very strong magnetic field. Your body is made out of water molecules. They're themselves little dipoles that now, kind of like your little compasses, that now will line up with that external magnetic field. And that's what, you know, it gets more complicated than that, exactly how that gives you eventually an image of what's going on inside. But that's what helps then determine, gives us an image of inside of your body. So one big solenoid. All right. Okay, so here's a question for you to think about. Basically kind of using this ideas of right-hand rule and magnetic field strength. All right, so let's take one wire and now let's bend it. So if you take a current carrying wire and bend it like shown here, Now assume that these two are actually right on top of each other. So you take a wire and you really place them on top of each other. I drew them slightly separate just to make it, to kind of really show that it's all one wire that was bent, but really picture that there's no separation here. So now I'm asking you, what is the magnetic field at this point A? So think about this. All right, so how do we approach this? So first of all, think about, as electric field obeys a principle of superposition, so does magnetic field. So you can think of these, this current going to the right and to the left as if there's two sources. So you can figure out what is the magnetic field due to the bottom part of the wire and what's the magnetic field due to the top part of the wire, and then add those two magnetic field vectors. So it's not a simple addition, it's a vector addition. So if we look at point A here, what do we, let's think about direction first. So if we focus on the bottom part of the wire, the current is going down, our fingers will curl this way, so that means at point A, our fingers point into the board. So I think maybe next slide I have it. Yeah. Okay, so here we go. So from the bottom part here, our magnetic field is pointing into the board. Now from the top part of the wire, now the current is going to the left. Fingers curl in such a way it's going over the wire, curling underneath, coming out of the board at me. See my fingers pointing at me from the top. So we have two vectors, one into the board, one out of the board. So they're in opposite direction, but that's not necessarily enough to make them zero as you see the answer. What else has to be satisfied to make them zero is that not only do they have to be in opposite direction, they have to have the same magnitude. But what does magnitude at point A depend on? It depends on, well, the current, but it's one wire, so it's going to have the same current. And also the distance. And because they're touching, that's why I really kind of stress the fact, imagine they're touching, point A is really the same distance from the bottom and the top. So in other words, they are opposite of equal magnitude, so they will cancel and you will actually get a zero magnetic field. Now, as a kind of additional thought process, imagine they weren't touching and imagine this distance was significant. What would that tell us? That would tell us that the contribution of the magnetic field from the top, that one that goes out of the board, would be smaller because point A would be farther away from the top segment compared to the bottom segment. So if the one coming out of the board is smaller than the one coming into the board would be bigger. So when you subtract those two, the into the board wins, so you get a magnetic field into the board in that case. So it's just a good kind of follow-up thought process. But in this case, when they are perfectly on top of each other, touching each other, they will have the same magnitude, same strength, same distance away from the wire, opposite direction, so the sum of the two will be zero. All right, so kind of making connections, more connections between magnetism and electricity. So what we've just learned is that electric currents, so moving charges, create magnetic fields. So in a sense, we had moving charge, that was sort of our source that created a magnetic field. So let's now ask a question, well, what does a magnetic field do to electric current? So imagine now we kind of reverse the situation. Instead of having a current that's creating a magnetic field, if we had a magnetic field now present due to something else, a magnet or maybe another wire, and if we had charge sitting there, will it do something to the charge? And it seems like, again, and laws of nature are very symmetric, that indeed something should happen, that magnetic field should affect electric current. So we're going to look at it from that perspective. So instead of looking at current as a whole, let's just start with putting our charge inside of a magnetic field. So if we start with this situation, so we have some external magnetic field and we have, in this case, a positive charge and it's not moving, magnetic field doesn't do anything to it, turns out. So what we're basically trying to figure out is what forces are exerted on our charges due to magnetic fields. Now, if we had a charge which was moving parallel to the magnetic field, so what did we find with our currents before? That when we had like a current, the magnetic field was generated. There was no magnetic field component which was parallel to the current. There were circles around, so it was always kind of perpendicular to that current. So how does that translate to this situation? If we had a magnetic field, and if our charge was moving along the side of a magnetic field, again, there's no effect. So it doesn't do anything. This charge does not feel this magnetic field. There's no force. It just keeps on moving in a straight line. However, if our charge was moving, well, in this picture, it's perpendicular, but in general, at any angle except parallel or anti-parallel to a magnetic field, then there would be a force that that charge would feel in the presence of that magnetic field. That force is known as the Lorentz force, and it obeys this equation. So let's take a look at it. So what you see on this picture is that there's a magnetic field pointing that way, the blue arrow. There is the velocity vector pointing this way to the right, and then the force seems to be going up. So that's direction. So we'll get to that next. The Lorentz force equation here that I wrote here is just for the magnitude. How strong is that force? What does it depend on? Well, it depends on the actual charge, Q. Actually, it should be absolute value here because it doesn't, this is just magnitude. So the whole thing should be in absolute values. It's just telling us how big is the force. It depends on the speed. So the faster your charge is moving, the bigger will be the force. It depends also on the strength of the magnetic field. The stronger that magnetic field, the stronger the force. And it also depends on that angle. So this theta is the angle between B and V. So how do we maximize the force? When the sine of theta is 1 is when theta is 90 degrees. So when they're perpendicular, that's when you get the biggest force. When they're parallel, when theta is 0, we get no force, as we just saw in the previous picture. So, but you can have an angle less, anywhere between 0 and 90, you would still get a force, just not as strong as you would if they were perfectly perpendicular to each other. All right, so this is what tells us about magnitude. How do we figure out the direction? It seems like the three things are perpendicular to each other in this picture. We use, guess what, another right-hand rule. So this is normally known as right-hand rule number 2, and that's for the Lorentz force. So there's two ways that I think it's done a little bit different in DL. I just wanted to show you a different way because I kind of like it more. So this is the flat palm method to figuring out the direction of the force. So what you do is you put your thumb, where this V is, in the direction of the speed of the charge. So if my charge is moving that way, then your fingers point in the direction of the magnetic field, and then which way your palm kind of pushes is going to be the direction of the force. So I like this because it really kind of stresses the fact that your palm is pushing. So this is how this picture kind of helps you figure out that method. So the one that you maybe learned at DL is with a 3 fingers, sometimes is known as the very bad finger. So the way this one works is that you actually, instead of using the palm, you use fingers. So the thumb still goes in the direction of the velocity. This finger goes in the direction of the magnetic field, and then this finger, so you see the 3 are perpendicular to each other, kind of similar to what you see in the picture, will then stick up. And then you can imagine as this, let's say V and B change, then the direction of the force will change too. So the palm method is really the same, except instead of separating these fingers, you just point all the fingers towards B, and then instead of lifting the finger, you push the palm, and that gives you that force. So whichever method you're comfortable with, it's fine. All right. So one thing though, so again, this was just magnitude, how big the force is. The right-hand rule is direction, but you know, we have learned that positive and negative charges are different. So it would be kind of counterintuitive if both positive and negative charges felt the same force, and they don't, in fact. So this right-hand rule is only for positive charges. If your charge is negative, you still use the same exact right-hand rules, this one. So for example, if this V was now a negative charge, you still use this right-hand rule, you figure out the forces up, but that's true for a positive charge. Because your charge is negative, you flip your answer 180 degrees. So the correct answer is the force is down. So you still, again, use the right-hand rule, same methods you use, but you then don't forget, because it's a negative charge, to flip your answer. So if you got your force to the right, but it was a negative charge, then the answer is to the left, and so on, up, down. So that's how you deal with the negative charges. So this gives you the magnitude. This is all just a positive, has to be a positive number. And then right-hand rule gives you direction, flip it for a negative charge. Okay, so how do we use actually a right-hand rule if the angle is not perfectly perpendicular? Because, you know, this is the sine of theta, so it doesn't have to be 90 degrees. Well, what this tells us, this b sine theta, it really says that the only component of your b vector that matters is the one that is perpendicular to velocity. So you would still, to use the right-hand rule, you would still make these two fingers perpendicular. It's just keeping in mind that what you're thinking about is not b, the direction of b itself, but the direction of b sine theta. So that component which is perpendicular. So you don't need to worry about like readjusting your fingers because the angle is not perpendicular. You always treat them as if they're perpendicular when applying the right-hand rule. So let's do it for this actually picture. So here we have V pointing up. So again, the component of B that will matter will be to the right. So what do we get? My palm is pushing now into the screen. So our force from this perspective is into the board if the charge is positive. If the charge was negative, we would have to flip the direction, and then we would conclude that the force is coming out of the board. So this is how we apply, you know, right-hand rule number 2. So number 1 is the one that has to do with current and figuring out the direction of magnetic field around wires, and this has to do with forces on charges due to external magnetic fields. All right, let's practice a little bit, mostly the right-hand rule. So now we have a negative charge. Be careful, remember what I just told you. So we have a negative charge which is moving in a magnetic field, as shown here. The magnetic field is pointing to the left. What is the direction of the force on the charge? So here's a little cheat sheet for you, the right-hand rule. Think about this, practice your right-hand rule. All right, so let's do it. V, which is my thumb, points up. Ignore for now, it's a negative charge. So now, you know, my fingers are already pointing towards B, which is towards the left. Which way is the force? My palm is pushing me towards me. So the force is out of the board, but it's a negative charge, so we have to flip it. So the answer is A, into the board. Again, this just takes some practice. It's really unfortunate. The one unfortunate thing about me not being in the real classroom this quarter is that there's some really cool demos that all of 7C out of the 3 classes in the Physics 7, I think, have the most interesting and cool demos, and that's something that I've really been missing doing. There were a lot of fun ones with interference and waves that I couldn't do, and then with this magnetism, it seems so abstract, you know, charges and magnets, but there's a cool demo where I show you like a cathode ray tube with a bunch of electrons moving that you could see, and I bring a magnet close, and you actually see this path deflecting, because in fact charges do feel forces in external magnetic fields. So it becomes more convincing, I guess, more visual when you see this demonstration. So it's too bad. All right. Okay, here's another cool thing. So here it's a little bit trickier. Because you have to, now here's a hint, you need to use both right-hand rules to figure out. So the question is, you're shown here two wires, and by the way, you know, it's not like this wire ends, you kind of just picture it continuously moving in space, like this current is going up in this direction and down in this direction. So shown here are two current carrying wires, and what you're trying to figure out is there force on A on this wire A? So there's nothing else in space out there, just these two wires. Does wire A feel a force? Maybe it doesn't, maybe it does. So think about why you would need to use both right-hand rules. So what did we learn? So we learned that magnetic fields, so current generates magnetic fields, and then charges feel those magnetic fields. So what you have to think about this is this way. We're focusing on wire A. How could wire A feel a force if, well, it could feel a force because there are charges that are moving, and we know that moving charges feel forces in magnetic fields. Is there a magnetic field here? Well, yes, because this wire B generates a magnetic field. So what we have to figure out here is, what is the magnetic field generated by B? In which direction is it at the location of A? So you could think about wire B sort of our source, and wire A, or the charges in wire A, are tests that are feeling that source. So B generates a magnetic field everywhere in space, but we only care about where is it, what's the direction of a magnetic field at the location of wire A. Once we know that we have a bunch of charges. Current, remember, is the motion of positive charge. So we have a bunch of positive charges that are moving. So they have a velocity pointing upwards in the direction of that, in the presence of that magnetic field. So we can use our second right-hand rule to figure out force. So let's think about this. And I find that, so that's the answer, but let's go over it. I find that this is a little bit easier to solve or to visualize if you change the perspective. So let's look at the top view. So I just took these two wires and I'm looking at them at the top. So wire A is this one here with current coming towards me out of the board, and wire B has the opposite current going into the board. So what we have to do again is use our right-hand rule number one first to figure out the magnetic field. So B, wire B, the current points into the board, my fingers curl around, so you get this clockwise magnetic field. So over here, the magnetic field, tangent line will point up like this. Now, the charges in current A are coming out of the board. So you put, now I'm using my second right-hand rule. These out of the board, my fingers point up in the direction of B, which way my palm is pushing, to the left. So that's how we get that answer, which is to the left. Again, current is positive charge, so we don't need to worry about flipping the sign. Just using the right-hand rule and getting that answer is enough. So what we see actually is these two wires will repel each other, because wire A will move away from wire B, and you can do the same type of analysis for wire B due to wire A, and you will find that the force, and I recommend you do this, you should find that the force on B due to the magnetic field generated by A will be to the right, so the two will repel. And one thing I suggest you do at home as an exercise is figure out, will this situation change, and if it does, how, if the two currents were in the same direction. So instead of opposite, let's say B was also up, or both A and B were down. So think about this and figure out the direction of the force. All right, a lot of information today. Hope you enjoyed. I think I'm done for today. Have fun watching it. All right, oops. I need to stop.